Hello, this is going to be a lesson A10, variation in problem solving. Direct variation. If you ever hear the words y varies directly with x or y is directly proportional with x, you want to think about an equation like this: y equals kx, where k represents a constant of variation. Okay, so let's suppose I have this example number 1. Suppose that y varies directly with x. So right there I see a keyword, varies directly, and I'll automatically think of y equals kx. Okay. If y is 5 when x is 30, find the constant variation in the direct variation equation. So basically the problem is giving us y and x and is telling us to find k. So basically all we're going to do is plug it in. So y is 5 equals k, and x happens to be 30. In order to get to k alone, I'm going to divide both sides by 30. The 30 cancels. We're left with k equals 5 over 30. So basically that's our answer, and we're done. Well, this is I apologize. This is part of our answer because it's asking for the constant variation, and that's what we found. Now, the other part is to find the equation. Well, the equation has this format, y equals kx, and we found out that k is 5 over 30. So basically this is our equation. Okay. Alright, very well. Now, we're going to do the next problem. And before we do that, we're going to talk about something called the Hooke's Law. The Hooke's Law tells us that the distance a spring stretches is directly proportional to the weight it is attached. So let's say I have a spring, something that looks like this, and is attached to a weight. So let's say there's a little weight right there, and that means when the weight is attached, the spring is going to stretch. So in other words, it might stretch like that when you have your weight attached, right? And so the Hooke's Law tells us that the stretching is proportional to the weight. So the heavier the weight, the longer the stretch is going to be. Okay, with that in mind, we're going to do the next example. Next example says, if a 40-pound weight is attached to a spring, then the spring stretches 5 inches. Find the distance that a 65-pound weight stretches. According to the law, we know that it's directly proportional. So in other words, before we do this, let's kind of come over here. Directly proportional reminds us that it's going to have this format. Okay. Well, let's get the k alone by dividing both sides by x. So x goes away. So this would be y over x. And basically what this means, the k is a constant. So it doesn't matter, like let's say this was 5 pounds, and let's say I had another one that was like 10 pounds. So the stretch would be bigger. Okay. So let's say here it is stretched by, let's say, 6. Okay. And over here it would stretch by 12. Because as you can see, 5 over 6 would be the same as 10 over 12. Okay, basically that's what this is saying. Okay, is that doesn't matter, the situation is going to be a constant. It's going to always be the same. So basically, here I have a situation. If a 40-pound weight is attached to a spring, then the spring stretches 5 inches. So if I have 40 pounds, the stretching is going to be 5 inches, right? And the question is, find the distance that a 65-pound stretches. So let's suppose I have a bigger weight, 65 pounds, and what is going to be the stretching? So basically what it means is the 5 over 40 is going to be the same as x over 65. Basically what it's saying is the two quantities that we're looking at here, if we put them as a fraction, it's going to be a constant. So if I have this over this, it's going to be the same as this over this. And let's say I have another number, let's say an even bigger weight. The stretch over the weight is going to be the same as this over this over this, because according to the Hooke's law, the distance that a spring stretches is directly proportional to the weight. So that means the stretch over the weight is always going to give you the same number. Doesn't matter the numbers. I mean, it doesn't matter how big the weight can be or how small it can be. When you take the stretch divided by the weight, is always going to be a constant. That's what this means, okay? And because that means that, we can always set up a proportion. And once we can set up a proportion, basically we can solve for x. So this would be 40x equals 5 times 65. We're going to divide both sides by 40. X equals 5 times 65. Just a moment here. Let me get my calculator. 5 times 65. Give me a second here. My calculator is not working. Okay. 5 times 65 divided by 40 is 8.125 inches. Okay? Very well. Alright, let's go on to the next part of this lesson. Okay? We're going to talk now about inverse variation. Okay? If you remember, direct variation was y equals kx. Inverse variation is going to be y equals k times 1 over x, or you can write y equals k over x. Okay, either way is the same. But basically inverse variations, that means the x is going to be on the bottom. If it was direct variation, the x is on the top. Okay, so if anytime you see varies inversely or is inversely proportional to x, you need to think about x being on the denominator. Okay? So suppose I have a problem like this. Suppose that u varies inversely with w. So that means u equals k, and because it says inversely, w is going to be on the bottom. And if u is 3, then w is 5. So if this is 3, then the w will be equals 5. And question is, find the constant variation and the inverse variation equation. So basically, I'm going to get the k alone by multiplying both sides by 5. So this would be 15 equals k. So that means our constant is 15. And our equation, basically, is this guy right here. And since we found out k to be 15, so then this would be u equals 15 over w. So that's our equation. Okay. Alright, let's go on to the next problem. Well, before we do that, we have a new law to talk about. We're going to talk about Boyle's law. Boyle's law has to do with if the temperature stays the same, the pressure P of a gas is inversely proportional to the volume. Okay? So, in other words, P equals K over V. Alright? And if you would get the K alone, we would multiply V on both sides, so this would be K equals P times V. Okay? So basically, Boyle's law says that the pressure times the volume is always equals a constant. Okay, so there's a whole idea here about Boyle's law. So basically, this we have this problem here. If a cylinder in a steam engine has a pressure of 9060 kilopascal when the volume is 1.4 meters cubic meters, find the pressure when the volume increases to 2.5. Okay, if you think about a cylinder, right? You have the cylinder here, and they have like a little chamber here, okay? And this will represent your volume, okay? And sometimes the cylinder has that amount of space for the gas, and sometimes it has little space, okay? Alright. So basically what the Boyle's law says, when you have a bigger volume, the pressure is going to be smaller. And when you have a smaller volume, you're going to have a higher pressure. So means the bigger the volume, the less the pressure. The smaller the volume, the higher the pressure. So there's an inverse proportion. Okay? Alright. So with that in mind, and according to what we found out here, the pressure times the volume is always equals a constant. So if I have a let's say this guy here is the 2.5 this is the 1.4, right? Meter, there's the volume, right? And here I have the 2.5 meter, the cubic meter, and this here represents I'm going to have a pressure of 960. And the question is, how much is my pressure going to be here? So notice that if I take the pressure times the volume here, that's going to equal a constant, and that constant is the same as if I multiply the pressure times the volume of this other situation here. So in other words, PV equals PV. So in other words, the pressure here it will be X, and the volume would be 2.5, and the pressure on this one would be 960, and the volume would be 1.4. So here's an equation where I can solve for X, and that's the power of having that constant there. Basically, it'll allow us to say this is the same as that. Okay, so this would be going to get the X alone by dividing by 2.5. So X equals 960 times 1.5. Times 1.4 divided by 2.5 is 537.6 kilopascal. Okay. Alright, very well. Okay. The last variation we're going to talk about is called the joint variation. Let me bring this to view. And basically, what does it have to do is like when you have more than just two quantities, you have three quantities. Okay, so let's say I have y, x, and z. And so if you ever see varies jointly or jointly proportional, you know that you're going to have not one variable here, but you have more than one. Okay. So Suppose I have this problem. It says y varies jointly as x in the square of z. So that means that you would have y equals k, you have x, and you have z squared. And then the problem says if y equals 360, plug it in that information. So x here would be 4, and the z would be 3 to the second power. So basically here this would be 360 equals k times 3 squared is 9 times 4 is 36. We're going to solve for k, so we're going to divide both sides by 36. 36 goes away, k equals 10. So that's my constant variation. That's what the problem asks. And now all I need to do is do my equation, which is y equals k x z squared. So this would be y equals 10 x z squared. Okay. Alright, and then the last variation will be the combined variation, which is basically a combination of direct, inverse, and joint variation. Basically, you need to watch out for those keywords. So for example here, the maximum weight that a circular column can support is directly proportional. So here we have the maximum weight, so we're going to start with W, is directly proportional. So we start with a K. Directly proportional means you're gonna the quantity is gonna be here on top. So what is the quantity? The fourth power of its diameter, so it'd be d to the fourth, and is inversely proportional. Inversely proportional means going to be on the bottom. And what is the quantity? Inversely proportional to the square of its height. So that means the height will be raised to the square, and it's going to be on the bottom. So basically we're talking about this relationship. Okay? The weight equals a constant times the diameter to the fourth times the height. Okay? Basically what is it talking about is, imagine like a column of concrete. Okay? And basically we're putting weight over here on top of the column to see how much weight it will withstand. Okay? This is very there's a very practical use for this. This is used a lot in civil engineering, where they want to find out how much a column of concrete can withstand, how much weight, so that way they will know how big the column has to be in order to withstand the traffic on top of that column. Okay, so for example, one time in engineering school, we would see different labs that they had like this big machine that would take these little columns of concrete. Now they were like small columns, okay, and they would put this machine on top of it, and this machine would had a big arm over here, and it would push down on that column until that column break. And that will give the engineers or future engineers an idea of how to predict which columns would be good for certain bridges and certain construction projects that they have. Okay, so basically what this problem does is talking about this. Okay, it tells us that these columns have a constant variation. So let's go ahead and first get that constant variation by itself. So let's say I multiply both sides by, let me erase that circle that I put in there. It's making, so let's say I have this, and I'm going to get that k alone. So first I'm going to multiply by h squared on both sides. So this would be h squared w equals k d to the fourth. Alright, now I want to get the k alone, so I'm going to divide by d to the fourth. And that cancels, so I'm left with k. Alright. Okay, So what we found in this equation here that there is a constant variation. Okay. So that means on the lab at the university, they can measure little columns, and with that, so that means that the little column at the college lab would have a smaller diameter and a much smaller height, but we'll be able to use all this information to then make a prediction. For example, on a bigger column, how much would the height and the diameter have to be for a certain weight? And that's the power of this information. So let's go back to this problem here. Okay, most of the problems on this section is going to have two situations. Okay, and let's look at these two situations. A 2-meter diameter column that is 8 meters in height can support 1 ton. So in other words, I have one situation that can be represented by this, and because this is always constant, I can compare that to another situation that the problem is going to talk about. The other situation would be find the weight that a 1 meter diameter and 40 meter high column can support. So basically, on all these problems, you're going to have two situations, and all you have to do is plug it in and see what value is missing. So let's look. A 2 meter diameter, so we have the diameter for the first, so it would be 2 to the 4th. That is 8 meters high, so we have the height, which is 8 squared, and can support a weight of 1. Okay. And find the weight, so we need to find the weight that a 1 meter diameter, so 1 meter diameter, and 4 meter high column, high column can support. So basically, if you notice here, I'm looking at the first situation equals the second situation. Okay, and basically I'm having one piece of information missing, and that way I can solve for that missing piece. Alright, 8 squared is 64. 2 to the 4th power will be 16. This would be 16W, and 1 to the 4th power is 1. Alright, I'm gonna 64 divided by 16 is what is 64 divided by 16? Is 4. And this would be 16W. And to get the W alone, all you have to do is divide it by 16. So 16 goes away, and you get W equals 4. Okay, so that means for the weight that this column can support, the column that has a 1 meter diameter and a 4 meter high column, can be only 4 pounds. Okay, alright, so this concludes the lesson for variations. So thank you very much for your time, and have a great day.